Light travels at an incredible speed, approximately 299,792,458 meters per second. This speed is so fast that it can circle the Earth more than 7 times in just 1 second. Imagine the sheer velocity at which light moves, making it the fastest thing in the universe. This speed is the ultimate speed limit in the universe, according to Einstein's theory of relativity. Einstein's groundbreaking work showed that nothing can surpass this cosmic speed barrier. It's a fundamental aspect of how our universe operates. Nothing with mass can ever reach the speed of light. As objects move faster and faster, they require more and more energy to continue accelerating. This is why even our fastest jets and rockets can't come close to light speed. As an object approaches the speed of light, its mass increases infinitely. This means that the closer you get to light speed, the heavier you become, making it harder to accelerate further. This makes it increasingly difficult to accelerate further. The energy required to keep pushing an object closer to the speed of light becomes astronomical. Reaching the speed of light would require an infinite amount of energy, which is impossible. Our current technology and understanding of physics simply can't overcome this barrier. The speed of light is not just a limit, it is a fundamental constant in physics. It is a cornerstone of our understanding of the universe, influencing everything from the behavior of particles to the expansion of the cosmos. It governs the way light and other electromagnetic waves propagate through space. This constant speed ensures that the laws of physics remain consistent across the universe. Its significance extends to many areas of physics, from cosmology to quantum mechanics. Understanding the speed of light helps us unlock the mysteries of the universe, from the smallest particles to the vastness of space. Imagine you could chase a beam of light. What would you see? As you approach the speed of light, the light beam doesn't appear to slow down. This is because the speed of light is constant for all observers, regardless of their relative motion. Instead of the light slowing down, the space in front of you would appear to contract. This effect, known as length contraction, is a consequence of special relativity. The faster you move, the more space contracts in the direction of your motion. Additionally, time would slow down for you relative to a stationary observer. This phenomenon, known as time dilation, is another bizarre consequence of special relativity. At speeds close to the speed of light, our vision would be dramatically altered. The world as we know it would transform into something almost unrecognizable. Everyday objects and landscapes would take on new and bizarre appearances, challenging our perception of reality. One of the most striking effects is the Doppler shift. This phenomenon, which we commonly associate with sound, also applies to light. As we move closer to the speed of light, the colors of the world around us would begin to change in unexpected ways. Just like the pitch of a siren changes as it moves towards or away from us, the color of light changes depending on its motion relative to the observer. This is due to the compression and stretching of light waves, which alters their frequency and, consequently, their color. As we approach the speed of light, the wavelengths of light in front of us would be compressed, causing a blue shift. This means that objects in our path would appear increasingly blue as we accelerate. The faster we go, the more pronounced this effect becomes. Objects would appear bluer than they normally would. The sky, the ocean, and even the mountains would take on a surreal, almost otherworldly blue hue, making the world look like a scene from a science fiction movie. Conversely, the wavelengths of light behind us would be stretched, causing a red shift, making objects appear redder. The landscape we leave behind would be bathed in deep, rich reds, as if perpetually caught in the glow of a setting sun. Furthermore, an effect called relativistic aberration would come into play. This effect, a direct consequence of traveling at such high speeds, would drastically alter our field of view. This effect would cause our field of view to distort and compress, concentrating objects towards the direction of our motion. The faster we go, the more our vision would narrow, creating a tunnel-like effect. It would be like looking through a fisheye lens with the entire universe seemingly squeezed into a tunnel in front of us. Stars, planets, and galaxies would all appear to converge towards a single point, creating a visually stunning yet disorienting experience. This is the reality of seeing in warp speed, where the very fabric of space and time bends to the will of our motion. Einstein's theory of special relativity proposes a mind-bending concept. Time is not absolute but is relative to the observer's frame of reference. This revolutionary idea changed our understanding of the universe and how we perceive time. This means that time can pass at different rates for observers who are moving relative to each other. For instance, if one person is standing still while another is moving quickly, they will experience time differently. Imagine two perfectly synchronized clocks, one on Earth and one on a spaceship, traveling at a significant fraction of the speed of light. As the spaceship accelerates, the clock on board starts to tick more slowly compared to the one on Earth. According to special relativity, time would pass slower on the spaceship compared to Earth. This effect becomes more noticeable as the spaceship's speed increases. This means that when the spaceship returns to Earth, the astronauts would have aged less than the people who stayed behind. Less time will have passed for the clock on the spaceship than for the clock on Earth. This discrepancy is a direct consequence of time dilation. This phenomenon, known as time dilation, is not just a theoretical concept. It has been experimentally verified using atomic clocks. Scientists have placed synchronized atomic clocks on airplanes and observed that the clocks on the planes ticked more slowly than those on the ground. It is a real effect that becomes more pronounced as objects approach the speed of light. This has profound implications for our understanding of space travel and the nature of the universe itself. The faster we move, the more time seems to stretch and warp, revealing the intricate and fascinating relationship between time and motion. Section 5. A wrinkle in time dilation. To understand time dilation, imagine time as a flowing river. On Earth, we experience time flowing at a normal rate, like drifting down a calm river. However, as we approach the speed of light, it's like our boat starts moving incredibly fast along the river. The faster we move, the less time we spend drifting downstream or experiencing time. For someone standing on the riverbank, a stationary observer, time continues to flow normally. This analogy illustrates how our motion through space affects our motion through time. The faster we move through space, the slower we move through time relative to someone at rest. Section 6. The Twin Paradox, a Spacefaring Tale. One of the most famous thought experiments illustrating time dilation is the twin paradox. Imagine two identical twins. One twin stays on Earth, while the other embarks on a high-speed journey through space. Upon the traveling twins' return, they would find that they are younger than their Earth-bound sibling. This is because time passed slower for the traveling twin due to their high speed. While seemingly paradoxical, this outcome has been experimentally verified. It highlights the reality of time dilation and its profound implications for space travel. Section 7. Black holes, where time stands still. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. According to general relativity, time is also affected by gravity. The stronger the gravitational field, the slower time passes. At the event horizon of a black hole, the point of no return, time comes to a standstill. This means that if you were to observe an object falling into a black hole, you would see it freeze in time at the event horizon. While we cannot directly observe what happens inside a black hole, our current understanding of physics suggests that time behaves very differently in these extreme environments. Section 8. The Quest for Time Travel. Possibilities and Paradoxes. The concept of time travel has fascinated humankind for centuries. While time travel into the future is possible within the framework of special relativity, time travel to the past remains a topic of debate and speculation. One of the most significant challenges to backward time travel is the grandfather paradox. This paradox asks what would happen if you went back in time and prevented your grandparents from meeting. If they never met, you would never have been born, so how could you go back in time in the first place? While many solutions to the grandfather paradox have been proposed, including alternate timelines and self-consistent universes, a definitive answer remains elusive. Section 9. Conclusion. The speed of light and the future of exploration. The speed of light is not just a physical limit, but a fundamental aspect of the universe that governs the way we perceive and experience time and space. Its implications for space travel and our understanding of the cosmos are profound. While reaching or exceeding the speed of light remains a distant dream, our exploration of these concepts continues to push the boundaries of human knowledge. As we delve deeper into the mysteries of the universe, we may one day unlock the secrets of time travel and interstellar travel, opening up new frontiers of exploration and discovery.